You've probably heard that the speed of light is a constant, right? That nothing in the universe can travel faster than light, and that this speed never changes. It's one of those fundamental truths we learned in school, a cornerstone of modern physics. But what if I told you that the reality is far more strange, more complex, and more mind-bending than you ever imagined? What if the speed of light isn't quite what you think it is? And here is a question for you. If you could travel at the speed of light to any point in the universe, where would you want to go? Let me know in the comments. I will pin the most creative answer. Now let's begin. When we talk about the speed of light, we're discussing something profound. We're talking about approximately 299,792,458 meters per second. That's roughly 186,282 miles every single second. But here's where things get interesting. This number, this cosmic speed limit, isn't just about light zipping through space. It's about the very fabric of reality itself. Think about it for a moment. Light from the sun takes about 8 minutes and 20 seconds to reach your eyes. That means when you look up at our star, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. You're looking into the past. Every ray of sunlight touching your skin left the sun's surface before you even decided to step outside. This isn't science fiction. This is the universe showing you one of its most fundamental characteristics. Time and space are connected in ways that challenge our everyday intuition. But let's dig deeper, because the speed of light becomes even stranger when you start to examine what scientists have discovered over the past century. Albert Einstein, back in 1905, proposed something revolutionary in his special theory of relativity. He suggested that the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. This was radical. It meant that if you're standing still and measure the speed of a light beam, and then you jump on a spaceship traveling at 90%, the speed of light, and measure that same beam, you'll get the exact same number. It doesn't matter how fast you're moving. Light always moves at the same speed relative to you. This leads to some wild consequences. Time dilation, for instance. If you were to travel close to the speed of light, time would literally slow down for you compared to someone standing still. You could travel for what feels like a few years, return to Earth, and find that decades or even centuries have passed. Your twin who stayed home would be much older than you, or perhaps not even alive anymore. This isn't theoretical speculation anymore. We've measured time dilation with atomic clocks on airplanes and satellites. GPS satellites have to account for these relativistic effects, or your navigation would be off by miles. Now here's where your understanding might start to shift. The speed of light isn't just a speed limit for light, it's a speed limit for information, for causality itself. Nothing can carry information faster than light travels through a vacuum. This cosmic speed limit is woven into the structure of space-time. It's not that light is special in some magical way. Rather, light moves at this speed because photons, the particles of light, have no mass. Any particle without mass must travel at this ultimate cosmic velocity. But wait, there's a twist. When we say the speed of light is constant, we're specifically talking about light traveling through a vacuum, through empty space. When light passes through materials like water, glass, or even air, it slows down. This happens because light interacts with the atoms in those materials. In water, light travels at about 75% of its vacuum speed. In diamond, it's even slower, roughly 40%. This slowing effect is why a straw looks bent when you put it in a glass of water. The light changes speed as it moves from air into water, causing it to bend, a phenomenon called refraction. Scientists have pushed this even further. In carefully prepared laboratory conditions, researchers have slowed light down to just 17 meters per second, slower than a car on a residential street. They've even brought light to a complete stop, trapped it, and then released it again. These experiments involve ultra-cold atoms and quantum mechanics, and they're expanding our understanding of light's behavior in ways that could revolutionize technology. If you're finding this journey through the cosmos as fascinating as I do, please hit that subscribe button and give this video a thumbs up. Creating content that explores the mysteries of our universe takes time and research, and your engagement helps this channel grow. Now, we've established that light slows down in materials, but in the vacuum of space, it's always the same speed, right? Well, here's where modern cosmology throws us another curveball. Some scientists are asking whether the speed of light has always been constant throughout the entire history of the universe. Could it have been different in the early moments after the Big Bang? Could it vary across vast cosmic distances? These aren't fringe ideas from the edges of science. These are serious questions being explored by researchers using data from our most advanced telescopes. The James Webb Space Telescope, humanity's most powerful eye on the distant universe, is sending back data that's challenging some of our long-held assumptions. When astronomers look at light from galaxies billions of light years away, they're seeing those galaxies as they were billions of years ago. The light has been traveling through space for most of the universe's history to reach us. By analyzing this ancient light, scientists can test whether the fundamental constants of physics, including the speed of light, have remained truly constant. Recent studies published in 2024 have attempted to measure the speed of light using cosmological observations, things like Type Ia supernovae, the cosmic microwave background, and gravitational waves. These measurements are getting more precise, with some suggesting we'll soon be able to test whether the speed of light measured across cosmic distances matches what we measure in laboratories here on Earth to within about 1 to 2% accuracy. That might not sound impressive, but measuring a fundamental constant of nature across billions of years of cosmic history is an extraordinary achievement. There's something called the cosmological horizon problem that makes physicists wonder about the early universe. Imagine the universe right after the Big Bang. Different regions of space that were too far apart to have ever exchanged light or information somehow ended up with nearly identical properties, the same temperature, the same density, the same physical characteristics. How could regions that never communicated with each other be so perfectly synchronized? One proposed solution is called inflation, a period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang. But some scientists have proposed an alternative. What if the speed of light was much faster in those early moments? This idea, called variable speed of light cosmology, suggests that the cosmic speed limit might not have always been what it is today. If light traveled faster in the early universe, distant regions could have communicated and reached equilibrium before inflation supposedly occurred. Now, this remains a controversial hypothesis. Most physicists still favor the standard inflation model, but the fact that serious scientists are exploring this possibility shows us something important. The speed of light, as fundamental as it seems, is not beyond questioning. Let me share something that might blow your mind even more. The universe itself can expand faster than light. I know what you're thinking. Didn't we just say nothing can travel faster than light? Here's the thing. Einstein's speed limit applies to objects moving through space, but space itself can stretch and expand at any rate. Think of it like this. Imagine two dots on a balloon. As you inflate the balloon, the dots move apart, not because they're moving across the rubber, but because the rubber itself is stretching. That's what's happening with the universe. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This is called Hubble's law, discovered by Edwin Hubble back in 1929. Galaxies beyond a certain distance are moving away from us faster than light because the space between us and them is expanding so rapidly. This doesn't violate relativity because nothing is actually moving through space faster than light. the space itself is growing. This means there are galaxies we will never be able to see no matter how long we wait or how powerful our telescopes become. Their light will never reach us because the space between us is expanding too quickly. The current estimate for the expansion rate of the universe is called the Hubble constant, and here's where things get controversial. When astronomers measure this expansion by looking at nearby cosmic objects, they get one number. When they calculate it using the cosmic microwave background radiation from the early universe, they get a different number. This discrepancy, called the Hubble tension, is one of the biggest mysteries in modern cosmology. Some scientists wonder if our understanding of the speed of light over cosmic distances might play a role in resolving this puzzle. Now, while we're on the subject of cosmic speed limits and the strange ways the universe defies our intuition, you might be wondering if there are any theoretical ways to get around this ultimate barrier. Actually, I made an entire video exploring this question called "Scientists Propose a New Way to Travel Faster Than Light." It dives into the cutting-edge theories and wild ideas physicists are exploring, from warp drives to wormholes. If the concept of breaking or bending the cosmic speed limit fascinates you, definitely check that out after this video. The link is in the description and on the card above. But let's get back to light itself and explore another mind-bending aspect. When we measure the speed of light, what exactly are we measuring? This question is more subtle than it seems. In a vacuum, light travels in a straight line at constant speed, but the universe isn't empty. It's filled with gravitational fields from stars, planets, black holes, and dark matter. Einstein's general theory of relativity, published in 1915, tells us that massive objects curve spacetime itself. Light follows the curves of this warped spacetime, taking what's called a geodesic, the shortest path through curved space. This means that light passing near a massive object like the Sun will bend around it. We've observed this effect, called gravitational lensing, countless times. During a total solar eclipse in 1919, astronomers led by Arthur Eddington observed stars near the Sun's edge and found their positions shifted, exactly as Einstein's theory predicted. The light from those stars had curved around the Sun's gravitational field. This observation made Einstein famous overnight and revolutionized our understanding of gravity. But here's the truly weird part. From the light's perspective, if a photon could have a perspective, it's always traveling in a straight line at constant speed through flat space. It's the space itself that's curved. An observer far away sees the light path as bent, but locally, right where the light is, space-time looks flat and the light moves straight ahead. This is one of the beautiful and strange insights of general relativity. Gravity isn't a force pulling on objects. It's the curvature of space-time itself, and objects, including light, simply follow the curves. Gravitational fields do something else remarkable to light. They slow down time. Imagine a light beam climbing out of a deep gravitational well, like escaping from near a black hole. To an outside observer, that light appears to take longer to travel a certain distance. Time itself runs slower in stronger gravitational fields. This effect is called gravitational time dilation, and it's another prediction of general relativity that we've confirmed through precise experiments. Atomic clocks at different altitudes on Earth tick at slightly different rates. A clock on a mountaintop runs faster than one at sea level because it's farther from Earth's mass and experiences weaker gravity. Black holes take this to the extreme. At the event horizon, the boundary beyond which nothing can escape a black hole, time effectively stops from the perspective of a distant observer. If you could watch someone fall into a black hole, you'd see them slow down as they approach the event horizon, their image becoming redder and dimmer, frozen in time just at the edge. Meanwhile, from the perspective of the person falling in, they would cross the horizon in finite time and continue toward the singularity at the center. Time becomes deeply relative in these extreme environments. This brings us to another fascinating aspect of light's journey through the cosmos. Light doesn't just travel, it carries information about everything it encounters along the way. When light from a distant galaxy reaches our telescopes, it tells us about the galaxy's composition, temperature, motion, and age. It also tells us about everything between that galaxy and us. As light travels through intergalactic space, it passes through clouds of gas, encounters magnetic fields, and stretches along with the expansion of the universe itself. Each of these interactions leaves a signature, a fingerprint that astronomers can decode. When light passes through hydrogen gas, for instance, certain wavelengths get absorbed, creating dark lines in the spectrum. By studying these absorption lines, scientists can map out the invisible matter between galaxies, the cosmic web of gas and dark matter that connects everything in the universe. One of the most powerful techniques in modern astronomy relies on something called redshift. As the universe expands, the wavelengths of light traveling through it get stretched. Blue light can become red light. Infrared light can stretch into microwaves. The amount of stretching tells us how much the universe has expanded since that light began its journey. This means astronomers can use redshift as a cosmic clock, measuring distances and ages across billions of years. The most distant galaxies we've observed have redshift so extreme that their ultraviolet light has been stretched all the way into the infrared, which is exactly why the James Webb Space Telescope, built to see infrared light, is revolutionizing our view of the early universe. But here's something that challenges our intuition even further. When you look at a galaxy that's, say, 13 billion light-years away, that doesn't mean the galaxy is 13 billion light-years away right now, because the universe has been expanding the entire time that light was traveling toward us. That galaxy is actually much farther away now, perhaps 30 billion light-years or more. The light you're seeing left that galaxy when the universe was much younger and smaller, and both you and that galaxy have been carried apart by cosmic expansion ever since. Distance and time become intertwined in cosmology in ways that make simple measurements extraordinarily complex. Now, let's talk about something even more fundamental. What exactly is light? You might think you know the answer, but light has a dual nature that puzzled scientists for centuries. Is it a wave or a particle? The answer, strangely enough, is both. This wave-particle duality is one of the central mysteries of quantum mechanics. In some experiments, light behaves like a wave, spreading out, creating interference patterns, diffracting around obstacles. In other experiments, light behaves like a stream of particles called photons, discrete packets of energy that can be counted one by one. This duality isn't just an academic curiosity. It's fundamental to how the universe works at the smallest scales. When a photon is traveling through space, it exists in a quantum superposition, taking all possible paths simultaneously. Only when it interacts with something, when it's measured or absorbed, does it collapse into a definite position and path. This quantum weirdness applies to all particles, not just light, but photons are often the easiest way to demonstrate these bizarre effects. The famous double-slit experiment illustrates this beautifully. Fire photons one at a time at a barrier with two narrow slits. You might expect each photon to go through one slit or the other, creating two bright spots on a detector screen behind the barrier, but that's not what happens. Instead, an interference pattern emerges, alternating bright and dark bands, as if each individual photon went through both slits simultaneously and interfered with itself. The wave nature of light creates this pattern, but if you place a detector at the slits to see which one each photon goes through, the interference pattern disappears. The act of measurement forces the photon to choose a path, and it behaves like a particle. Observer and observed are connected in quantum mechanics in ways that still spark philosophical debates. Now let's connect this back to the speed of light. In quantum field theory, the modern framework that combines quantum mechanics and special relativity, light is understood as an excitation of the electromagnetic field that permeates all of space. A photon is a quantum of this field, a ripple in the electromagnetic fabric of the universe. This field has a property, a characteristic impedance that determines how fast electromagnetic waves, including light, can propagate through vacuum. The speed of light emerges from the fundamental properties of space itself, specifically from two constants, the permittivity and permeability of free space. These describe how space responds to electric and magnetic fields. What this means is profound. The speed of light isn't some arbitrary number that nature happened to choose. It's built into the structure of spacetime and the laws of electromagnetism. Maxwell's equations, formulated by James Clerk. Maxwell in the 1860s predicted the existence of electromagnetic waves and calculated their speed based purely on measurements of electric and magnetic forces. When Maxwell did the math, the speed came out to be about 300 million meters per second. This was a stunning revelation. Light, electricity, and magnetism were all manifestations of the same underlying phenomenon. This unification was one of the greatest intellectual achievements in physics, and it paved the way for Einstein's relativity. Maxwell's equations showed that electromagnetic waves, including light, always travel at the same speed, regardless of the motion of the source. This contradicted the prevailing notion that there must be some absolute reference frame, some cosmic ether through which light waves propagated. Einstein took Maxwell's equations seriously and built his theory of special relativity on the principle that the speed of light is constant in all reference frames. Here's another twist that might surprise you. Although we call it the speed of light, it's really the speed of causality, the maximum rate at which cause and effect can propagate through the universe. Anything without mass must travel at this speed. Photons do because they're massless. But so do gluons, the particles that carry the strong nuclear force, and gravitons, the hypothetical particles of gravity, if they exist, would also move at this cosmic speed limit. Even information encoded in gravitational waves travels at the speed of light, something that was spectacularly confirmed in 2017. On August 17, 2017, gravitational wave detectors LIGO and Virgo detected the collision of two neutron stars. Just 1.7 seconds later, gamma-ray telescopes detected a burst of light from the same event. These signals had traveled across 130 million light-years of space, and they arrived within seconds of each other. This observation confirmed that gravitational waves and light travel at essentially the same speed, providing powerful evidence for Einstein's theory of general relativity and constraining any possible differences to less than 1 part in a quadrillion. This detection opened up an entirely new field called multi-messenger astronomy. By observing cosmic events through multiple channels, gravitational waves, light across the spectrum, neutrinos, and cosmic rays, astronomers can piece together a more complete picture of the universe's most energetic phenomena. And all of these messengers are constrained by the same cosmic speed limit, or in the case of neutrinos, which have tiny masses, very close to it. Speaking of neutrinos, these ghost-like particles are another fascinating piece of the cosmic puzzle. Neutrinos are produced in enormous quantities by nuclear reactions in stars, including our Sun. Right now, trillions of neutrinos from the Sun are passing through your body every second, but they barely interact with ordinary matter. A neutrino could pass through a light year of solid lead without hitting anything. For many years, scientists thought neutrinos were massless and therefore traveled at exactly the speed of light. But experiments in the late 1990s and early 2000s revealed that neutrinos have tiny but non-zero masses. This means they must travel slightly slower than light. the discovery that neutrinos have mass was revolutionary. It earned the Nobel Prize in Physics in 2015 and demonstrated that even our most fundamental theories need updating as new evidence emerges. The fact that neutrinos travel just a hair below the speed of light has practical implications too. In 1987, when a supernova exploded in a nearby galaxy called the Large Magellanic Cloud, detectors on Earth picked up a burst of neutrinos. About 3 hours later, the light from that same explosion reached us. The neutrinos arrived first, not because they traveled faster, but because they escaped the star's core immediately when it collapsed, while the light took time to fight its way out through the outer layers of the dying star. This early warning system gives astronomers a heads up that a supernova is happening. Now let's explore something truly at the edge of physics, the question of whether light could ever actually be stopped, or whether anything could surpass it. We mentioned earlier that scientists have slowed light dramatically in laboratory experiments. In 1999, physicist Lena Howe and her team at Harvard University slowed light to just 17 meters per second by passing it through a cloud of ultra-cold sodium atoms in a state called a Bose-Einstein condensate. 2 years later, in 2001, her team succeeded in bringing light to a complete stop, storing it, and then releasing it again without losing the information it carried. These experiments rely on quantum mechanical effects, where the atoms are prepared in special states that dramatically change how they interact with light. The light essentially gets absorbed and re-emitted in a coordinated way that drastically reduces the group velocity, the speed at which the peak of a light pulse travels. This isn't violating relativity because the individual photons are still interacting with atoms at normal speeds. What slows down is the effective propagation of the light pulse through the medium. Still, the technological implications are enormous. Being able to stop and store light could revolutionize quantum computing and communication. On the flip side, can anything exceed the speed of light? In a vacuum, the answer according to our current understanding is no, not if you're talking about moving information or matter from one place to another. But the universe has some loopholes that are worth exploring. We already discussed how space itself can expand faster than light. There are also quantum phenomena that seem to involve faster-than-light correlations. When two particles become quantum entangled, measuring one instantly affects the measurement outcome of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and it bothered him deeply. However, and this is crucial, quantum entanglement cannot be used to transmit information faster than light. The correlations between entangled particles are purely statistical. You can't encode a message and send it instantaneously using entanglement. When you measure one particle, you get a random result, and the other particle's measurement will be correlated with yours, but you need classical communication which travels at or below the speed of light to compare results and see the correlation. So while entanglement is strange and non-local, it doesn't violate causality or allow faster-than-light communication. Then there are theoretical concepts like warp drives and wormholes. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's field equations that would allow a spacecraft to travel faster than light by contracting space in front of it and expanding space behind it. The ship itself wouldn't move through space faster than light. Instead, it would surf on a wave of spacetime, and space would carry it along. The catch is that creating such a warp bubble would require exotic matter with negative energy density, something we've never observed and may not exist in the quantities needed. Still, the fact that general relativity even allows such solutions shows that the universe might be stranger than we currently comprehend. Wormholes are another theoretical possibility, shortcuts through space-time that could connect distant regions of the universe. If you could create and stabilize a wormhole, you might step through and emerge light years away instantly. Again, this doesn't violate the local speed limit because you're not traveling faster than light through space. You're taking a shortcut through a different topology of space-time. But like warp drives, stabilizing a wormhole would likely require exotic matter and energies far beyond anything we can currently manipulate. These remain firmly in the realm of theoretical speculation, but they remind us that general relativity, as well tested as it is, contains possibilities we haven't yet ruled out. Let's bring this back to observable reality. One of the most important things about the speed of light is that it defines the observable universe. Because the universe has a finite age, approximately 13.8 billion years, and because light travels at a finite speed, there's a limit to how far we can see. Light from objects beyond a certain distance hasn't had time to reach us yet. This boundary is called the cosmological horizon, and it's constantly expanding as the universe ages, and more light has time to arrive. But here's the twist we touched on earlier. Because the universe is expanding, the actual radius of the observable universe is larger than 13.8 billion light-years. It's currently estimated at about 46.5 billion light-years in every direction. That means the observable universe is a sphere roughly 93 billion light-years across. Beyond that horizon, there's more universe, possibly infinitely more, but we can never see it. The light from those regions will never reach us because the expansion of space carries them away faster than light can travel toward us. This creates a profound form of cosmic loneliness. There are galaxies out there that we will never observe, civilizations that could exist that we could never contact, events happening right now that we'll never know about. The speed of light doesn't just set a limit on how fast we can travel or communicate, it fundamentally limits what we can know about the universe. Every observation we make, every piece of data we collect, is constrained by this cosmic speed limit and the finite age of the universe. Yet within the boundaries of what we can observe, light brings us extraordinary gifts. Every photon that reaches your eye or hits a telescope detector is a messenger from across space and time. The light from distant stars carries the story of nuclear fusion, of atoms being forged in stellar furnaces. The light from galaxies billions of light-years away shows us the universe as it was when it was young, allowing us to study cosmic evolution. The cosmic microwave background radiation, light that's been traveling since just 380,000 years after the Big Bang, gives us a baby picture of the universe itself. When you look up at the night sky, you're not just seeing stars as they are, you're seeing them as they were. The light from Proxima Centauri, our nearest stellar neighbor, left that star about 4 years ago. The light from stars in the Andromeda Galaxy began its journey 2.5 million years ago, when our ancestors were just learning to make stone tools. The light from the most distant galaxies observed by the James Webb Space Telescope has been traveling for over 13 billion years, showing us galaxies that formed when the universe was less than 5% of its current age. This time travel aspect of light is one of the most poetic and profound aspects of astronomy. We are quite literally observers of history. Every telescope is a time machine looking backward through the ages. The deeper we look into space, the further back in time we see. This allows astronomers to study how galaxies formed and evolved, how stars were born and died, how the chemical elements that make up our bodies were created and dispersed through space. The speed of light, by being finite, gives us access to the universe's entire history. But there's a limit to how far back we can see with light. In the earliest moments of the universe, for roughly the first 380,000 years, the cosmos was so hot and dense that it was opaque. Free electrons scattered photons constantly, preventing light from traveling in straight lines. The universe was a glowing fog. Only when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms did space become transparent. The light that was freed at that moment has been traveling ever since, stretched by cosmic expansion into the microwave part of the spectrum. This is the cosmic microwave background, the oldest light we can observe, a faint glow coming from every direction in space. Detecting this ancient light was one of the greatest discoveries in cosmology. In 1964, Arno Penzias and Robert Wilson stumbled upon it while working with a radio antenna at Bell Labs. They found a persistent noise in their detector that came from all directions and wouldn't go away. After ruling out all other explanations, including pigeon droppings in their antenna, they realized they had discovered the afterglow of the Big Bang itself. This earned them the Nobel Prize in 1978 and provided powerful evidence for the Big Bang theory. Studying the cosmic microwave background has become a precision science. Satellites like COBE, WMAP, and Planck have mapped tiny temperature variations in this ancient light, fluctuations of only a few millionths of a degree. These tiny ripples represent the seeds of all cosmic structure, the slight density differences that would eventually grow into galaxies, stars, and planets. By analyzing the patterns in this light, cosmologists have determined the age, composition, and geometry of the universe with remarkable precision. The cosmic microwave background also gives us another way to test the constancy of the speed of light. If light traveled at different speeds in the early universe, it would affect the patterns we see in this radiation. So far, all observations are consistent with the speed of light being constant throughout cosmic history, but scientists continue to test this assumption with ever greater precision. The fact that we're even able to test fundamental constants across billions of years is a testament to human ingenuity and our ability to decode the messages written in light. Now let's talk about something that connects directly to your own existence. You are made of atoms that were forged inside stars. The carbon in your cells, the calcium in your bones, the iron in your blood, all of these elements were created by nuclear fusion in the cores of massive stars or in the explosive deaths of those stars as supernovae. When those stars died, they scattered these elements into space, where they eventually became part of the cloud of gas and dust that collapsed to form our solar system. You are, quite literally, made of stardust. But here's where the speed of light comes back into the story. The light that those ancient stars emitted carried energy away into space. Without this radiation, stars couldn't shine. The fusion reactions in a star's core generate enormous amounts of energy, creating intense pressure that holds the star up against its own gravity. This energy must escape, and it does so through light and other forms of radiation. But light doesn't just zip straight out from the core to the surface. In the dense interior of a star, photons are constantly absorbed and re-emitted by atoms, taking a random walk that can last thousands or even millions of years before finally reaching the surface and escaping into space. A photon created in the core of our Sun takes an estimated 170,000 years on average to random walk its way to the surface. Once it reaches the surface, it takes just 8 minutes and 20 seconds to travel the 93 million miles to Earth. So the sunlight warming your face right now was created in nuclear reactions that happened when humans were still in the Stone Age, but it only left the Sun's surface about 8 minutes ago. Time and light interweave in fascinating ways. The energy transport inside stars, mediated by light, determines their structure, their lifetime, and ultimately their fate. Massive stars burn through their fuel quickly, shining brilliantly, but dying young in spectacular supernova explosions. Smaller stars like our Sun burn slowly and steadily, living for billions of years. The tiniest stars, red dwarfs, are so miserly with their fuel that they can shine for trillions of years, far longer than the current age of the universe. All of these stellar life cycles are governed by the interplay between gravity, nuclear fusion, and the transport of energy through radiation and convection. When massive stars explode as supernovae, they briefly outshine entire galaxies. The light from these explosions carries information about the physics of stellar death and the creation of heavy elements, type Ia supernovae, which occur when white dwarf stars accumulate too much mass and explode, are particularly important to cosmology because they have remarkably consistent peak brightness. Astronomers use them as standard candles, measuring their apparent brightness to determine their distance. This technique, applied to supernovae across billions of light years, led to one of the most shocking discoveries in modern science. In 1998, two independent teams studying distant type Ia supernovae made an unexpected discovery. The supernovae were dimmer than expected, suggesting they were farther away than calculations predicted. This could only mean one thing. The expansion of the universe isn't slowing down as everyone expected, it's speeding up. Some unknown force, dubbed dark energy, is pushing the universe to expand faster and faster. This discovery earned the Nobel Prize in 2011 and revolutionized our understanding of the cosmos. Dark energy makes up roughly 68% of the total energy content of the universe, yet we have no idea what it is. Dark matter, the invisible substance that holds galaxies together through its gravity, accounts for another 27%. That means all the normal matter we can see, all the stars, planets, gas, dust, everything made of atoms, accounts for just 5% of the universe. We are living in a cosmos dominated by components we don't understand, and our knowledge of them comes from their effects on light and gravity. The accelerating expansion driven by dark energy has profound implications for the far future. As the universe continues to expand faster and faster, galaxies beyond our local group will be carried away from us at ever-increasing speeds. Eventually, they'll recede faster than light can travel toward us, disappearing beyond our cosmological horizon. In the incredibly distant future, trillions of years from now, an observer in our galaxy would see a much emptier universe, with only the merged remnants of our local cluster of galaxies visible, surrounded by darkness. This means that future civilizations, if any exist in that distant era, will look out at the cosmos and see an entirely different universe than we do. They'll see a static, lonely island of stars surrounded by black emptiness. Without the evidence we can see today, distant galaxies rushing away, the cosmic microwave background, the abundance of light elements created in the Big Bang, they might never discover that the universe had a beginning or that it's expanding. The light available to them would tell a fundamentally incomplete story. We are fortunate to live in an era when the universe is still revealing its history, when the light from distant cosmic epochs can still reach us. This idea highlights something crucial about science and knowledge. What we can know is constrained by what we can observe, and what we can observe is limited by the speed of light and the age and expansion of the universe. There may be aspects of reality that are forever beyond our ability to detect or measure. Yet within these constraints, the human mind has proven remarkably capable of unraveling cosmic mysteries. Through clever experiments, mathematical reasoning, and careful observation of light from across the universe, we've mapped out the story of existence from the Big Bang to today. Let's shift perspective for a moment and think about light not as a tool for observation, but as a fundamental phenomenon that shapes reality itself. Light isn't just something we use to see, it's an active participant in the physics of the universe. Radiation pressure from light, though tiny, can push on objects. This force is what pushes comet tails away from the sun, creating those beautiful streaming tails that always point away from our star, regardless of the comet's direction of travel. Scientists have even proposed using light sails, spacecraft pushed by sunlight or powerful lasers, as a method for interstellar travel. The Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, envisions sending tiny spacecraft to nearby star systems using exactly this principle. A powerful ground-based laser would push ultralight spacecraft equipped with reflective sails accelerating them to perhaps 20% of the speed of light. At that velocity, they could reach Proxima Centauri in about 20 years. This wouldn't violate any laws of physics. The spacecraft would still be traveling well below the cosmic speed limit, but it would represent humanity's first serious attempt at interstellar exploration. Of course, traveling at even 20% of light speed presents enormous challenges. At those velocities, even tiny dust particles become deadly projectiles carrying enormous kinetic energy. Cosmic radiation becomes more intense, communication delays stretch to years. A radio signal from a probe at Proxima Centauri would take 4 years to reach Earth. Ask a question, wait 4 years for the answer. This is the reality of cosmic distances and the finite speed of light. But these challenges don't make the dream impossible. They simply define the constraints within which we must work. Think about what it means that light connects us to the cosmos in this way. Every time you look at a star, photons that traveled for years or centuries or millennia are ending their journey in your eye, triggering chemical reactions in your retina that your brain interprets as light. Those photons left a distant sun, crossed the vast darkness of space, passed through Earth's atmosphere, and arrived at exactly the right place and time to meet you. There's something almost magical about that connection, even though it's pure physics. This connection goes deeper than just seeing. The light from the sun drives photosynthesis in plants, converting light energy into chemical energy that forms the base of nearly all food chains on Earth. The energy in your body right now came from sunlight captured by plants or by animals that ate plants. You are powered by starlight, converted through biology into the warmth of your body and the thoughts in your mind. The photons streaming from the sun sustain all life on Earth, maintaining our planet's temperature, driving weather patterns, and energizing ecosystems. Without the sun's light, Earth would be a frozen, lifeless rock drifting through the darkness. The fact that our planet orbits at just the right distance from a stable star, receiving just the right amount of light and heat, is one of the remarkable circumstances that makes life possible. Scientists searching for potentially habitable planets around other stars focus heavily on this Goldilocks zone, the region where liquid water can exist on a planet's surface. Too close to the star and water boils away, too far and it freezes solid. Light and distance from the light source determine habitability. As we search for life beyond Earth, light will be our primary tool. Astronomers use techniques like transit photometry, watching for the tiny dimming of a star's light when a planet passes in front of it. By measuring how much light the planet blocks and analyzing the starlight that passes through the planet's atmosphere, scientists can determine the planet's size, density, and even the composition of its atmosphere. If we detect certain combinations of gases like oxygen and methane together, it might indicate biological activity. We'll be detecting alien life if we find it by the subtle ways it changes the light passing through its planet's air. The James Webb Space Telescope is specifically designed for this kind of investigation. Its powerful infrared sensors can analyze the atmospheres of exoplanets, looking for biosignatures, chemical signs of life. In September 2022, JWST made its first detection of carbon dioxide in an exoplanet's atmosphere, demonstrating its capability to identify specific molecules light years away. Future observations will search for more complex organic molecules and combinations of gases that could indicate living processes. We're also listening for light in other ways. The search for extraterrestrial intelligence, SETI, scans the skies for artificial radio signals from other civilizations. Radio waves are just light with long wavelengths, and they travel at the same cosmic speed limit as visible light. If an alien civilization sent a powerful radio message toward Earth, it would travel at the speed of light, taking years or centuries or millennia to arrive depending on their distance. If we receive such a message and respond, the the conversation would unfold over timescales longer than human lifetimes. A question asked today might not be answered for generations. This raises profound questions about communication, patience, and the long-term thinking required for truly cosmic endeavors. Human civilization has existed for only a few thousand years. We've had radio technology for barely over a century. In cosmic terms, we're newborns just beginning to reach out and listen. Other civilizations, if they exist, might be millions or billions of years older than us. What could we possibly have to say to beings that advanced? What could they say to us that we would understand? Yet the attempt to search, to listen, to reach out is fundamentally human. We are curious creatures living on a small world orbiting an average star in a galaxy of hundreds of billions of stars in a universe of trillions of galaxies. The light reaching us from all those distant suns whispers that we might not be alone. Even if the universe is teeming with life, the vast distances and the finite speed of light mean that encounters would be rare, communication slow, and understanding difficult. But the possibility alone is enough to inspire wonder and drive exploration. Let's explore another dimension of light's strangeness. We've talked about how light behaves, how it travels, and what limits it faces. But there's another question worth asking. Why does light exist at all? What is it about the structure of reality that requires this phenomenon? The answer takes us into the deepest foundations of physics, into the realm of quantum fields and fundamental forces. In the modern understanding of physics, reality is built from fields that permeate all of space. There's an electromagnetic field, a gravitational field, fields for each type of particle. These aren't just mathematical abstractions. They're real, physical entities that contain energy and can interact with each other. A photon is a quantum excitation of the electromagnetic field, a ripple in this underlying fabric. When an electron drops from a higher energy level to a lower one in an atom, the electromagnetic field responds by creating a photon that carries away the excess energy. Light emerges from the quantum mechanics of fields and particles. This framework, called quantum field theory, has been tested with extraordinary precision. The predictions of quantum electrodynamics, the theory that describes how light and matter interact, have been confirmed to better than 1 part in a billion. It's one of the most accurate theories in all of science, yet it's also one of the strangest. At the quantum level, the electromagnetic field is constantly fluctuating, even in what we think of as empty space. These quantum fluctuations create temporary virtual photons that pop in and out of existence, borrowing energy from the vacuum for impossibly brief moments allowed by Heisenberg's uncertainty principle. These virtual photons aren't just mathematical curiosities, they have real, measurable effects. The Casimir effect, predicted in 1948 and confirmed experimentally, occurs when 2 metal plates are placed very close together in a vacuum. The quantum fluctuations of the electromagnetic field between the plates are restricted compared to the fluctuations outside, creating a tiny attractive force that pushes the plates together. This is empty space filled with virtual light, exerting a physical force. The vacuum isn't empty at all, it's seething with quantum activity. This quantum view of light and matter reveals something profound. At the most fundamental level, reality is far weirder than anything we experience in everyday life. Particles and waves are just different aspects of underlying quantum fields. Cause and effect become fuzzy at small scales. Empty space contains infinite energy in principle, though it's locked away in quantum fluctuations. The speed of light emerges from this quantum substrate as a fundamental property of how these fields interact and propagate disturbances. Some physicists have speculated that the speed of light might be connected to even deeper aspects of reality. What if space-time itself is not continuous but made of discrete units, tiny pixels of reality at the Planck scale, about 10 to the negative 35 meters, far smaller than anything we can currently measure. At that scale, quantum effects of gravity would become important, and our current theories break down. A quantum theory of gravity, something physicists have sought for decades, might reveal that the speed of light is related to the fundamental structure of these spacetime pixels. String theory, one candidate for such a quantum gravity theory, proposes that fundamental particles aren't point-like, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. In this framework, photons are particular vibrational modes of strings, and the speed of light emerges from the properties of these vibrations and the geometry of higher dimensional space that string theory requires. While string theory remains unproven and controversial, it represents an attempt to find deeper explanations for the constants and properties we observe, including the cosmic speed limit. Loop quantum gravity, another approach to quantum gravity, suggests that space itself is quantized into discrete loops at the Planck scale. In this view, the smooth space-time of general relativity is an approximation that breaks down at the smallest scales, much like how a TV screen looks smooth from a distance but reveals individual pixels up close. The speed of light in this framework would be related to how information propagates across this network of quantum loops. These ideas remain highly speculative, but they show how seriously physicists take the question of what determines the speed of light and why it has the value it does. Perhaps the most profound question is this: could the speed of light be different in other universes? The multiverse hypothesis, inspired by certain interpretations of quantum mechanics and by inflationary cosmology, suggests that our universe might be just one of countless universes, each with potentially different physical constants. In some universes, the speed of light might be faster or slower. In others, the fundamental forces might have different strengths, or different particles might exist. If this is true, then the speed of light in our universe might not be dictated by any deep logical necessity. It might simply be one possibility among many, and we find ourselves in a universe with this particular value because universes with very different values wouldn't permit the formation of stars, planets, and life. This is called the anthropic principle, the idea that we observe the physical constants we do because we couldn't exist to observe different ones. It's a controversial idea that some scientists find unsatisfying because it seems to give up on finding deeper explanations. But it might be the truth. Regardless of whether the multiverse exists, the speed of light in our universe has shaped everything about our reality. It determines how fast information can travel, how quickly chemical reactions occur, how stars shine, how atoms behave, and how the universe evolves. Change the speed of light significantly, and nothing would work the same way. Stars might not be stable, atoms might not form. The universe might collapse back on itself, or expand so rapidly that no structures could ever form. We live in a universe finely tuned, whether by design, chance, or selection, from a multiverse to permit complexity and life. This brings us back to you, reading these words, contemplating the speed of light and what it means. Your existence depends on countless cosmic coincidences and physical laws working together in precise ways. The light reaching your eyes right now, whether from a screen or reflected off a page, traveled at exactly the right speed to make vision possible. The chemical reactions in your brain that allow you to think and understand occur at rates determined by quantum mechanics and the speed at which electrons can rearrange. You are a pattern of matter and energy, organized in intricate ways, existing because the universe has certain properties and not others. There's something humbling and uplifting about this perspective. We are small, temporary arrangements of atoms on a small planet orbiting an ordinary star, yet we are arrangements of atoms capable of understanding atoms patterns capable of recognizing patterns, consciousness capable of contemplating consciousness. Through science, through the careful study of light and matter across cosmic distances and timescales, we've decoded the fundamental rules that govern reality. We've looked back in time to the birth of the universe. We've peered into the hearts of atoms and stars. We've discovered that we are made of stardust, connected to everything in the cosmos through physics and shared history. The speed of light isn't just a number in a textbook, it's a thread that weaves through every aspect of existence, from the quantum realm to the cosmic horizon, from the birth of the universe to this present moment. It connects you to distant galaxies, to ancient stars, to the fundamental structure of space-time itself. When you understand light, you understand something essential about the universe and your place within it. Now let's venture into some of the cutting-edge research that's pushing our understanding of light and its cosmic speed limit even further. Scientists around the world are conducting experiments and observations that test the boundaries of what we know, searching for any hint that our theories might be incomplete or that new physics might be waiting to be discovered. One fascinating area of research involves looking for potential variations in the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions. This constant is built from several fundamental quantities, including the speed of light, Planck's constant, and the charge of the electron. If this constant has changed over cosmic time, it would suggest that one or more of these fundamental quantities isn't truly constant. Astronomers have searched for such variations by studying the spectral lines of light from distant quasars, comparing the patterns to what we see in laboratories today. Some studies published in the early 2000s suggested possible tiny variations in the fine structure constant at different locations in the universe, creating headlines and controversy. However, more recent and comprehensive analyses, including data from the most advanced telescopes, have found no convincing evidence for such variations. As of 2025, the consensus is that the fine structure constant, and by extension the speed of light, appears to be truly constant across the observable universe and throughout cosmic history, at least within the limits of our measurement precision. But scientists keep looking because finding even a tiny variation would be revolutionary. It would indicate new physics beyond the standard model, perhaps pointing toward a theory of quantum gravity, or revealing connections between the fundamental forces that we don't currently understand. The absence of variation is itself an important result, telling us that our theories are remarkably robust and that the universe plays by consistent rules across vast distances and times. Another frontier involves the study of ultra-high-energy cosmic rays and gamma rays. When the most energetic particles and photons in the universe travel through space, they should interact with the cosmic microwave background and other radiation fields. These interactions depend on fundamental physics, including the speed of light and the structure of space-time. By studying how these ultra-energetic particles behave, scientists can test whether the laws of physics hold up at extreme energies far beyond what we can achieve in particle accelerators. Observatories like the Pierre Auger Observatory in Argentina and the High-Altitude Water Cherenkov Observatory in Mexico detect cosmic rays with energies millions of times greater than anything produced at the Large Hadron Collider. Some theories of quantum gravity predict that at these extreme energies, space-time itself might have a granular structure that would affect how particles propagate, potentially causing different wavelengths of light to travel at slightly different speeds. This would be a violation of Lorentz invariance, the principle underlying special relativity. So far, no such violations have been detected. Light at all energies, from radio waves to the highest energy gamma rays, travels at the same speed within the precision of our measurements. This puts strong constraints on many quantum gravity theories and tells us that if space-time does have a discrete structure, it must be at scales even smaller than current theories predict. The fact that we can use light from cosmic explosions billions of light years away to test fundamental physics is itself remarkable. The universe becomes our laboratory, conducting experiments at scales and energies impossible to achieve on Earth. Speaking of cosmic explosions, let's talk about gamma-ray bursts, the most luminous events in the universe since the Big Bang. These incredible eruptions occur when massive stars collapse into black holes or when neutron stars collide. For a few seconds or minutes, a gamma-ray burst can outshine all the stars in its host galaxy combined, releasing in moments as much energy as the Sun will emit over its entire 10 billion-year lifetime. The light from these explosions travels across billions of light-years to reach us, and by studying how different wavelengths arrive, scientists can test whether light's speed truly is independent of its energy. In particular, if higher energy photons traveled even slightly faster or slower than lower energy ones, we'd see a dispersion effect, with different colors arriving at different times after traveling for billions of years. Observations of gamma-ray bursts have put incredibly tight constraints on any such effect, confirming that the speed of light is independent of photon energy to extraordinary precision. These observations rule out many speculative theories and strengthen our confidence in the fundamental principles of relativity. Let me share something that might change how you think about time itself. Because the speed of light is finite and nothing can exceed it, the universe has a built-in speed limit for cause and effect. Events that are far enough apart in space cannot influence each other if they're too close together in time. This creates what physicists call light cones, geometric structures that define which events can causally affect which other events. Your past light cone contains all the events that could have influenced you, all the points in space-time from which light could have reached your current position. Your future light cone contains all the events that you could potentially influence. Outside your light cones lie events that are space-like separated from you, events happening right now according to some reference frames but which you cannot yet see or affect. The Andromeda Galaxy is about 2.5 million light-years away. Anything happening there right now won't be visible to us for 2.5 million years, and anything we do now won't affect Andromeda for the same amount of time. In a very real sense, there is no universal now, no cosmic present moment that applies everywhere. Simultaneity depends on your reference frame, and the finite speed of light ensures that causality remains well-defined even though time is relative. This structure of space-time, with its light cones and causal boundaries, means that the universe has a kind of speed limit built into its very geometry. You can't send signals to your past self to change history. You can't know what's happening right now in a distant galaxy. Information is bounded by light speed, and this preserves the logical consistency of cause and effect. Without this speed limit, causality itself might break down, leading to paradoxes and contradictions. The speed of light doesn't just limit how fast things move, it protects the rational structure of reality. Now let's consider how our understanding of light has evolved through history, because the journey to our current knowledge is itself a fascinating story of human curiosity and ingenuity. Ancient philosophers debated whether light was emitted by the eye or by objects. Some thought vision involved rays shooting out from our eyes to touch what we see. Others correctly understood that light comes from sources and reflects off objects to reach our eyes. These debates were settled through careful observation and experimentation, though it took centuries. In the 17th century, scientists began to suspect that light might have a finite speed rather than traveling instantaneously. A Danish astronomer made the first quantitative estimate in 1676 by observing the moons of Jupiter. He noticed that the times when the moons disappeared behind Jupiter varied depending on whether Earth was moving toward or away from Jupiter in its orbit. He correctly interpreted this as a light travel time effect and calculated a speed within about 25% of the correct value. This was extraordinary, determining the speed of something as fast as light using only observations of planetary moons and careful timing. Later experiments refined the measurement. In the 1840s, Hippolyte Fizeau used a rapidly spinning toothed wheel to measure light speed over a distance of several kilometers, getting impressively close to the modern value. Albert Michelson spent much of his career perfecting measurements of light speed, eventually achieving precision of better than 1 part in a million by the early 20th century. These painstaking measurements provided the foundation for Einstein's revolutionary theories. What's remarkable about the history of measuring light speed is how scientists went from crude estimates based on planetary observations to incredibly precise measurements that revealed fundamental truths about spacetime itself. Each generation of scientists built upon the work of those before, refining techniques, improving instruments, and asking deeper questions. This is how science progresses, through incremental advances and occasional revolutionary insights that reframe everything we thought we knew. Einstein's insight that the speed of light must be constant in all reference frames didn't come from new experimental data. It came from taking Maxwell's equations seriously and following the logic to its conclusion, even when that conclusion seemed absurd. Time dilation, length contraction, the equivalence of mass and energy, all of these revolutionary ideas flowed from one simple postulate. The laws of physics, including the speed of light, are the same for all observers, regardless of their motion. This was a triumph of theoretical reasoning, later confirmed by countless experiments. The experimental confirmations of relativity are numerous and compelling. Particle accelerators routinely accelerate particles to speeds approaching the speed of light, and the particles behave exactly as relativity predicts. Their masses increase, they experience time dilation, and they require exponentially more energy to accelerate as they approach light speed. GPS satellites orbiting Earth must account for both special and general relativistic effects. Their clocks run at different rates than clocks on the ground due to their velocity and the weaker gravitational field they experience. Without relativistic corrections, GPS positioning would drift by kilometers per day. The fact that GPS works is everyday proof that Einstein was right. Gravitational time dilation has been measured with extraordinary precision using atomic clocks. In 2010, physicists at NIST demonstrated that they could detect the time dilation effect from moving a clock just 1 foot higher in Earth's gravitational field. 1 foot. The difference in clock rates was only about 90 parts in 10 quintillion, but it was measurable. This shows both the power of modern experimental physics and the reality of relativity's predictions. Time literally runs at different rates depending on where you are and how fast you're moving. These effects, while tiny in everyday situations, become dramatic at high speeds or in strong gravitational fields. Near a black hole's event horizon, time slows to a crawl from an outside observer's perspective. A spaceship accelerating to near light speed would experience time passing much more slowly than it does on Earth. This is sometimes called the twin paradox. If one twin stays on Earth while the other travels at near light speed to a distant star and back, the traveling twin will have aged much less than the stay-at-home twin. This isn't just a thought experiment. It's been confirmed with atomic clocks flown on aircraft and with particles created in cosmic ray collisions that live far longer than they should because they're moving so fast. This brings up an interesting question about future space exploration. If humanity ever develops the technology to build spacecraft capable of traveling at a significant fraction of light speed, time dilation would become a practical consideration. A crew traveling at 90% of light speed would experience time passing at less than half the rate of people on Earth. They could travel to stars dozens of light years away and return within a human lifetime from their perspective, even though centuries would have passed on Earth. This creates fascinating scenarios for science fiction, but it's grounded in real physics. Of course, actually achieving such speeds presents enormous challenges. The energy required increases dramatically as you approach light speed. To accelerate even a small spacecraft to 90% of light speed would require energy equivalent to thousands of nuclear weapons. And as we mentioned earlier, colliding with even tiny dust particles at those speeds would be catastrophic. Interstellar travel at relativistic speeds isn't impossible in principle, but it would require technological capabilities far beyond anything we currently possess. Some scientists have explored whether we might somehow circumvent these limitations through exotic physics. The Alcubierre warp drive concept, for instance, proposes compressing space in front of a spacecraft while expanding it behind, allowing the ship to effectively travel faster than light without violating local physics. The spacetime itself moves, carrying the ship along. Inside the warp bubble, the ship wouldn't experience any acceleration or time dilation. From the ship's perspective, it would remain stationary while the universe moved around it. The problem is that creating such a warp bubble would require exotic matter with negative energy density and lots of it. Initial calculations suggested you'd need more energy than exists in the entire observable universe. More recent refinements have reduced the energy requirements, but they're still far beyond anything achievable with known physics and technology. Some physicists have even questioned whether such spacetime configurations are truly stable or whether quantum effects would destroy them. The warp drive remains firmly in the realm of speculation, but it's legitimate speculation grounded in solutions to Einstein's equations. Wormholes face similar challenges. While they're allowed by general relativity, keeping them open and stable would likely require exotic matter and enormous energies. Even if we could create or find a wormhole, traversing it safely would present additional problems. Some solutions to the equation suggest that information and possibly matter could travel through wormholes, potentially even backward in time, which creates causality paradoxes. Most physicists suspect that quantum effects or other unknown physics would prevent the formation of time-traveling wormholes, preserving causality, but we don't yet have a complete theory that can definitively answer these questions. These speculative ideas highlight an important point. Our current understanding of physics, as successful as it's been, is almost certainly incomplete. General relativity and quantum mechanics, our two most fundamental theories, are incompatible with each other in extreme conditions like the center of black holes or the moment of the Big Bang. We need a quantum theory of gravity to fully understand these situations, and such a theory might reveal new possibilities or constraints we haven't imagined. It's possible that future discoveries will show us ways around the cosmic speed limit that we can't currently conceive. It's also possible that the speed limit is truly absolute and no loopholes exist. Either way, the limit shapes our destiny as a species. If we're forever bound by light speed, the universe will always be vast and largely unreachable. If we find loopholes, the cosmos might eventually become accessible in ways we now think impossible. The answer matters not just for science fiction, but for the long-term future of intelligent life. Let's return to something more concrete and observable. One of the most beautiful phenomena involving light is the rainbow, something you've probably seen countless times, but which contains deep physics. When white light from the sun enters a water droplet, different wavelengths refract at slightly different angles because the speed of light in water depends slightly on wavelength. This dispersion separates the colors, and internal reflection inside the droplet sends them back out at specific angles, creating the arc of colors we see in the sky. The primary rainbow shows red on the outside and violet on the inside. Sometimes you can see a secondary rainbow above the primary, with colors reversed, caused by light that reflected twice inside the water droplets. The physics of rainbows involves the speed of light in different media, the geometry of spheres, and the wave nature of light. Something as simple and beautiful as a rainbow demonstrates fundamental properties of electromagnetic radiation. Every time light enters a different material, it slows down and changes direction, a process called refraction. This is why a straw in a glass of water looks bent at the water's surface. The light from the submerged part of the straw travels more slowly in water than in air, bending at the interface. Lenses work by precisely shaping transparent materials to control how light refracts, focusing it to create images. Your eyes contain biological lenses that focus light onto your retina. Eyeglasses correct for imperfections in this focusing. Telescopes and microscopes use carefully designed lens systems to magnify distant or tiny objects. The fact that light slows down in materials has practical applications beyond optics. In particle physics experiments, when charged particles travel through water or other transparent materials faster than light travels in that material, they emit a blue glow called Cherenkov radiation. This is the optical equivalent of a sonic boom, a shock wave of light created when a particle exceeds the local speed of light. Detectors use this radiation to identify and study particles created in high-energy collisions or cosmic ray interactions. Large neutrino detectors, like the Super Kamiokande detector in Japan or the Ice Cube Observatory at the South Pole, work by detecting Cherenkov light from neutrinos that occasionally interact with water or ice. These detectors contain thousands of light sensors watching for the characteristic flashes that signal a neutrino collision. Through this method, scientists have detected neutrinos from the Sun, from cosmic sources, and even from a supernova that exploded over 30 years ago. Light, in its various interactions with matter, becomes a tool for exploring the most elusive particles in nature. The speed of light also defines a fundamental form of loneliness. We are isolated in time and space by the finite rate at which information can travel. When you look at the night sky, you're seeing the past, not the present. The stars you observe might no longer exist. They might have exploded, collapsed into black holes, or simply burned out, but their light continues its journey across the void, carrying messages from epochs that have ended. You are receiving ghosts of light from distant pasts, and this is all you can ever receive. The true present state of distant objects is forever hidden behind the light speed barrier. This isolation extends to any potential contact with other civilizations. If intelligent life exists around other stars, we are separated not just by distance, but by time. A conversation with beings orbiting Alpha Centauri, our nearest stellar neighbor system, would involve an 8-year round-trip delay. A conversation with a civilization on the other side of the galaxy would span 100,000 years. Empires could rise and fall in the time it takes to receive a reply. This fundamentally shapes what contact with alien intelligence would mean if such contact ever occurs. Yet there's also something profound in the fact that we can observe the universe at all, that light reaches us from the most distant realms of space and time. The cosmic microwave background brings us information from when the universe was just 380,000 years old. Light from the earliest galaxies shows us the cosmos in its infancy. Through careful observation and analysis, we've reconstructed the entire history of the universe from a hot, dense beginning to the vast, cold, accelerating expansion we see today. The speed of light, by being finite, gives us access to history itself. Think about the fact that you exist in a particular moment of cosmic history, roughly 13.8 billion years after the Big Bang, on a planet orbiting a middle-aged star in a mature galaxy. This is a special time. The universe has cooled enough for complex structures to form, for stars and planets and life to exist, but it hasn't yet expanded so much that distant galaxies have disappeared beyond our horizon. We live in an era when the universe is observable, when we can study its origins and evolution, when the evidence of cosmic history is still available to those with the curiosity and tools to seek it. In the far future, trillions of years from now, the accelerating expansion driven by dark energy will have carried most galaxies beyond the cosmic horizon. An observer in that distant epoch would see a nearly empty universe, just the merged remnants of the local galaxy cluster surrounded by darkness. The cosmic microwave background would have redshifted into undetectability. The evidence that the universe had a beginning, that it's expanding, that it contains dark matter and dark energy would be much harder or impossible to find. We are fortunate to exist when we do, when the universe still reveals its secrets through the light that reaches us. This temporal perspective should inspire a certain humility and urgency. We have a window of opportunity to understand the cosmos, a window that is cosmically brief. Humanity has existed for a tiny fraction of cosmic history, and our scientific civilization for an even tinier fraction. Yet in this brief moment, we've managed to decode the fundamental laws of physics, to map the large-scale structure of the universe, to peer back to within a fraction of a second after the Big Bang. We've discovered that we are made of atoms forged in stars, that we live in an expanding universe filled with mysteries like dark matter and dark energy, that the speed of light connects and constrains everything we observe. What we do with this knowledge matters. The questions we ask, the observations we make, the theories we develop, all contribute to humanity's understanding of its place in the cosmos. Every time you look up at the night sky and feel wonder, every time you contemplate the vastness of space and time, you're participating in the same impulse that drove ancient astronomers to map the stars and modern scientists to probe the quantum realm. The desire to understand, to know why things are the way they are, is one of the most distinctly human characteristics. The speed of light, this fundamental constant that appears in equations throughout physics, represents something deeper than just a velocity. It's a window into the structure of reality itself. It tells us that space and time are not separate, but interwoven into space-time. It tells us that mass and energy are equivalent, related by that famous equation E mc2. It tells us that information and causality have limits, that the universe operates by rules that are consistent and comprehensible. Every photon that reaches your eye from a distant star carries these truths encoded in its journey. As I bring this exploration to a close, consider one final thought. You began reading this text some time ago, and in that time, light has traveled thousands or millions of kilometers from the sun, has bounced countless times between atoms in the atmosphere, has been absorbed and re-emitted by the molecules in your retina. The electrical signals in your brain that represent thoughts and understanding travel far slower than light, carried by chemical and electrical processes in neurons, but they too are governed by the same fundamental physics, the same quantum mechanics and electromagnetism that governs everything else. You are a pattern of matter that has organized itself into something capable of contemplating light, speed, time, and existence. You are stardust arranged in such a way that the universe can know itself. The atoms in your body were forged in stellar furnaces, scattered across space, and eventually incorporated into a planet where conditions allowed life to emerge and evolve. Through billions of years of cosmic and biological evolution, matter became conscious, and consciousness turned its attention to understanding the universe that created it. The speed of light is one thread in this vast tapestry of existence. Pull on that thread, and you discover relativity, quantum mechanics, cosmology, the history of the universe, the nature of time, the possibility of life elsewhere, the limits of knowledge, and the structure of reality itself. Everything connects. Physics, astronomy, chemistry, biology, philosophy, all are different perspectives on the same unified cosmos, the same dance of matter and energy across space and time. So when you next see sunlight streaming through a window, or starlight twinkling in the night sky, or even just the glow of a screen illuminating these words, remember that you're witnessing something extraordinary. You're seeing electromagnetic radiation that traveled at the cosmic speed limit, the fastest that causality itself can propagate. You're seeing photons that might have been created in nuclear fusion in the sun's core hundreds of thousands of years ago, or in a distant star centuries or millennia ago, or in an LED microseconds ago. Each photon has its story, its journey, and they all end in your eye, in your awareness, connecting you to the universe in the most direct way possible. The speed of light is not just a fact to memorize or a constant to plug into equations. It's a fundamental feature of the cosmos that shapes everything from the smallest quantum interaction to the largest cosmic structures, from the briefest moment to the entire history of the universe. Understanding it means understanding something essential about existence itself. And why has no alien civilization visited Earth despite hundreds of billions of stars in the Milky Way? Check out the video at the left side of the screen and discover why Enrico Fermi's question of where everybody is remains unanswered despite NASA's space telescope discovering over 5,000 exoplanets, including Earth-like worlds in habitable zones. See you there.